Hi everyone. So today we'll talk about the soil texture. Welcome to the lecture 4. And so let's look at the this lecture note. The soil can be categorized into two groups. First one is the coarse grain soil. And versus fine grain soil. So first, coarse and fine. So you can see the difference, right? The difference will be the particle size. So there are many names that refers to the soil, like sand, gravel, cobble, clay, mud, silt, right? And when you align them in order in terms of the particle size, what will be the first one? What will be the biggest particle? That's gravel. And then we have sand, and you have silt and clay. So in terms of the particle size, gravel is the largest one, and then sand is next, and silt follows, and the clay has the smallest particle size. So in soil mechanics or the geotechnical engineering, we use these four names to refer the soil. So when we describe the soil, well, that's the sandy soil, that's gravelly soil, or that's silty soil, or that's clay soil, right? Or you can say that that's silty clay, or like silty sand, clay sand when it's mixed, right? So throughout this lecture 4 and 5 and 6, we'll see how we can classify the soil in terms of the particle size or some of the other characteristics. Today, we'll talk about the soil texture of the coarse grain soil. And coarse grain soil is typically we talk about sand and gravel. So here let me tell you the difference between gravel and sand. The difference between gravel and sand is the particle size. And if the particle or the grains are larger than 4.75 millimeter, as written in here, then it's gravel. If the particle size is less than 4.75 millimeter, then it's referred to as sand grains. Then, what about between the sand and silt? Engineeringly, in geotechnical engineering, we typically say that the smallest grain size that's visible to the naked eye is 75 micrometer. So if the particle is greater than 75 micrometer and less than 4.75 millimeter, then it's called a sand. If the soil is less than 75 micrometer diameter, then it's called the fine grain soil. And in lecture 5, we're going to talk about the fine grain soil later. So it's good to remember the 75 micrometer is kind of a threshold particle size that differentiate the coarse grain soil and the fine grain soil. So then when we talk the coarse grain soil and fine grain soil, the biggest difference is that the particle size, and as you have a bigger particle size, it's more affected by the gravitation, so by its weight. So then for the coarse grain soil, the particle size and their distribution and particle shapes play important role in characterizing their behavior. On the other hand, for the coarse grain soil, because the particle size is very small, the gravitational force is relatively, their contribution becomes smaller. On the other hand, the electrical force between the particle or maybe between the water and particle becomes more and more important. So because of that, interaction with the water, like electrostatic force, or the water content, and plasticity will play a role in determining their behavior in fine-grained soil. So we're going to talk about this later in lecture 5. Today we'll more discuss about the grain size distribution. Okay. So soils are made of, or originated from a rock, right? And I can show you a rock here, right? And here. And when we talk about the rock, we don't care the grain size or the particle size, right? Because it's all cemented and it's just a one rock. But as I showed you before, the sand grain, right? These are the sand, and the particle size becomes important. So we need to know what's the main particle size that's consisting this soil. Right? So to do that, we have to examine or identify the grain size distribution. It's called the GSD, or in short, or the particle size distribution. To examine or to identify the grain size distribution, we use sieve. Sieve analysis. And do you know what sieves are? Sieve is like this kind of a mesh. So woven wire square mesh that has a specific opening size. So when we have a soil, then using this sieve, you can identify that whether the soil is the soil grains are bigger than this opening, the sieve opening, or the less than the sieve opening. If it's less than sieve opening, then it's gonna pass this sieve, and if it's bigger than that, then it will be retained on this sieve. So there are several threshold size for the border between boulders and cobble. 30 centimeter, so 300 millimeter is the threshold size, and cobble and gravel is 7.5 centimeter, so 75 millimeter, and gravel and sand is 4.75 millimeter, and between the fine grain soil and the sand is 0.075 millimeter, so 75 micrometer. It's important to remember these numbers, especially this one and this one. And for the sieve opening size, because the particle is not like sphere, right? So it can have kind of elliptical particle size, particle shape, or it can be platy, or it could be very like sharpy or angular. So for irregular shape, we just use the opening size as the equivalent diameter, just to make it simple. So when we speak of the particle size or diameter, particle diameter, we mean an equivalent diameter determined by the sieve opening size. That's what here it says. Okay. And there are different sieves with various opening size, and this is the one that differentiate the gravel and sand. And so the opening size is about 4.75 millimeters. So it says here 4.75. You'll get to see it in the lab session. And I have a smaller one here. Maybe I can show you here, right? And opening side, I don't know if you can see it here. It says 850 micrometer, so 0.85 millimeter. And I have this one on the top, and this one is a little bit smaller, right? 425 micrometer, sieve number 40, right? So sieve number 40 is here, right? I think that this one is sieve number 20. And then what do I have? I have sieve number 100. So this is the sieve number 100, and the opening size is 150. So this is the one. And what else? And I have more. This is 140. And opening size is 106 micrometer. And the last one that people typically use is the sieve number 200. And as I said, the opening size is 75 micrometer. So it kind of differentiates the fine grain soil from the sand. That goes to the bottom. And you have pan, right? This one at the bottom. So when you do the sieve analysis, you will have this kind of a stack of sieve, and you pour soil on the top, and then you do the shaking like this, right? So then the big particle will be retained on the top, and then the one next, and the finest particle will pass the number 200 sieve, and it's gonna be retained in the pan, right? So we'll see which one is passing which sieve. Huh? So that's called the sieve analysis. Okay, so let's look at the handout. This one. The handout shows the different sieve with the various opening size. So here's the sieve number 400, and here's the sieve number 200, and the opening size, as I said, the 200 has the 75 micrometer, and number 4 sieve has the 4.75 millimeter. Huh? So above it, it's gravel. Below, it's sand up to this part, right? And below the 75 micrometer, it's fine grain soil. Right? So then, when you do the sieve analysis, so you have a total. You should measure, for example, you should measure the total mass of the soil, right? And then you're gonna pour it on the top and shake it. So then, after all the shaking, so that there's not any more the leftover soil that has not passed or has not retained, then you have each soil mass retained on each sieve, right? And so mass retained on each sieve is called the MRI, M sub R, I. And so if the some mass M2, MR2 is the mass of soil retained on the sieve number 2, right? So then, so you have this all the mass, and you can compute the cumulative mass retained on that. So when you add this one M1, and here the M1 plus M2, and here M1 plus M2 plus M3 plus 2MI, and then another one, and the last one will be the total mass. So then if you divide it by the total mass, then it gives you the percent cumulative mass on that corresponding sieve. And the final number that we want to get is the percent passing. So percent passing is 100 minus percent cumulative mass. Right? Then from that you can plot a distribution like this here. So I have, yep. Okay, we can go back to here. So we have a total mass which is mt, and the mass retained on the ith sleeve is mri, and you can determine the percent passing or percent finer than the corresponding ith sleeve. Then you can plot it in the semi-log space. So the x-axis is the particle size in log scale, and y-axis is the percent passing in linear scale. So let me give you an example. So let's say that the number 200 sieve, which is about 0.75, right? 0.075. So let's say that the mass of the soil that passed 200 sieve is 10%. So that means that among your soil, 10% the mass fraction is less than this 200 sieve opening size. And for example, like here is the number 4 sieve, and 90% has passed it. So then that means that the 90% mass fraction of your soil has the particle size less than 4.75 millimeter, because the opening size of the sieve number 4 is 4.75 millimeter. Okay, so then you can draw this kind of a grain size distribution curve, right? So you have a like smooth curve, or you can have like very sharp curve, or the steep, or the gentle slope curve. Then how can we characterize the grain size distribution? So first of all, let's imagine that we have two different soil, like soil A and soil B, as shown in here in this figure. And so soil A shows a kind of gentle slope over a wide range of the particle size, and soil B has very steep curve over a very narrow range of the particle size, right? So soil A means that it contains like small particle and medium-sized particle and a large particle, and soil B only have like very uniform or the very narrow like range, the particle size range. So then which one is called well graded and poorly graded? We call the soil A is well graded soil. So that means that the particle is here, the soil A has a small particle and large particles and medium-sized particles like this. And soil B is called poorly graded one because it has only the particles with the similar size each other. So it doesn't have like big particle and the small particles. And this is called the gradation. So when people ask what's the gradation of the soil of that field, and it is asking you about whether it's well graded or poorly graded, right? So you can answer that, oh, that soil is very poorly graded, or that soil is very well graded. So well graded means that it's also the well sorted. So you have small to large particles like very evenly contained in the soil. Okay, we're gonna define like 3 more parameters to characterize the grain size distribution curve today. First one is the effective diameter. Sorry, diameter, effective diameter, and we used the symbol D10. And how do we compute the D10? D10 is defined as the 10%, the diameter that corresponds to the 10% of the sample passing by the weight. Okay? So when you have this kind of a grain size distribution curve, then here the y-axis is percent passing, right? Or percent finer. So then if you draw a line from the 10 horizontal line and then cross section, that the corresponding diameter is called the D10. So likewise, you can also define T60, T50, T30, T20, right? So for example, here, for this black curve, T60 will be here. Right? For this, the blue curve, it will have a different T60 and T10. Then why this T10 is important? T10 represents the diameter of small particle. So this relates to hydraulic conductivity, and hydraulic conductivity means that how well the water can penetrate or the flow through the soil. So if the D10 is very small, then for example the clay soil, then the particle size will be small, so that the D10 will be very small, so the permeability will be small. But if you think about the gravel, the D10 will be larger than the sand or than the clay, so that soil will permeate, the water will permeate that soil very well. So it will have a higher hydraulic conductivity or the permeability. Okay, then the second parameter that we use is coefficient of uniformity. And we use Cu as a symbol. And Cu is defined as T60 over T10. So it doesn't have dimension, right? So diameter divided by the diameter, so the unit will be cancelled each other. So this is unitless, or the dimensionless parameters. So let's go back to the curve here. What will be the D10 of the soil A? Let me use this one. Maybe here. And D60 will be here. Right? D60, D10. And for the soil B, D10 will be somewhere here, and D60 also very close to the D10. So then for the soil B, when you compute the uniformity, the coefficient of the uniformity, it's gonna be very close to 1. But for the soil A, because it's wide, so D10 is much larger than the D60 is much larger than the D10. So then it's gonna be bigger than like 4 or 5, right? It could be like 10. So if it's the well graded, Cu increases, so it has a large value, great value. And if it's poorly graded, then Cu is less than 3, so it will have very small value. If you have just one particle size, uniformly graded soil, then so the D10 will be the same with D20, D30, D60, right? Like this. If it's just a straight line, the vertical at right angle, then D10, D90, D50, D1, D10 will be the same, right? So then Cu will be 1. So greater Cu means that it's more well graded. Okay, let's move on. And the last parameter to characterize the grain size distribution curve is called the coefficient of curvature. And it's called the CC. So when you look at these 3 types of curve and 3 types of soil, A, B, and C, it has the same D60 and D10. So here, right? D10 and D60. So only using the Cu, the coefficient of uniformity, is not sufficient to characterize the grain size distribution. So to complement that, people have suggested this coefficient, the parameter, and this is defined as d30 square over d10 times d60. Again, diameter square, the length square is divided by the length and length, so it has no unit. No? Again, so you can see that now that using this CC, so A and B and C will have different coefficient of curvature. Right? Which one will have the biggest one? This one. So A, because the D30 will be the biggest. Right? For the A and B and C, the denominator will be the same. So the numerator, D30, for soil A has the biggest one. So CC of A will be the biggest. And then the B, C. So this coefficient of the curvature kind of define and characterize the shape of the curve. If it's concave curve, then you have higher CC. If it's convex curve, then it's called, it has lower CC. You don't want to have like too high CC and the too low CC for the well-graded sand. So typically, if to satisfy the well-graded soil, CC should be within a certain range that is from 1 to 3. So when it's from 1 to 3, we can roughly say that it's going to linear. It has a linear grain size distribution curve, and it's more like well-graded soil. Okay, let's look at the handout. So I've shown you how to get the sieve analysis, and if you do the sieve analysis, you get this kind of a grain size distribution curve. The y-axis is the percent passing by weight, so it shows the percent of the soil mass that passed a certain sieve opening size, or you can say that the finer than percent finer, and the x-axis is the grain diameter, or people use the opening size of the sieve. So then towards the left, it's fine soil, so you have a small particle size, and toward the right is bigger grain size. So it's cobble, gravel, and sand, and the fines. And here the fines are clay and silt. So here, this curve is more likely well-graded soil, and here the one with very steep slope is the uniformly graded soil. And when you have this kind of wiggle, that means that a certain range of the soil is absent. It's not there. So here, for example, in this gap-graded soil, you have the soil's particle mostly in this region, and also another one here in this region. So that you don't have much soil within this from 0.1 to 1 millimeter diameter. So it's called a gap graded because you have a gap in the particle size range. Okay, let's move on. And here, D10 particle diameter corresponding to 10% passing by weight. You can define, likewise, you can define the several particle diameter, like D10, D30, D60, and D50. Okay, especially the T50 is called the mean grain size, or mean particle size, because it represents the median value of the grain size. Okay. Here, this figure shows there are some different soils grain size distributions. First one here, this is you can say that it has a very clean log normal distribution in terms of the grain size diameter, and it's very grady soil. Right? And when it's skewed like this, so that many particles are in 1 millimeter diameter, but you don't have much other the particle size, so then it's called a poorly graded soil. And when one size dominates in that soil, it's called uniformly graded. And the two particles are dominant, particle sizes are dominant, and you have a gap in between, it's gap graded. And here the important lesson is that the steeper curve over a particular range, the more particles exist in that range. And the flatter curve, right? Flatter curve. So if like this here, if it's flat like this, and there's no particle in that size range, no. Coarse. That will be all for this lecture. So if I can recap again. So we talked about the soil texture and the particle size, the importance of the particle size in coarse grain soil. And for grain, to get the grain size distribution curve, we do the sieve analysis. Right? And we talked about how to get it. And there are three important parameters: effective diameter, and coefficient of uniformity, and coefficient of curvature, to characterize the grain size distribution curve. Okay, that will be all for today. I'll see you later.